Hello again. Got cut off at the end of that last one. Let's pick up where I left off. Hopefully we don't have any more technical difficulties. Just get a couple more things to go over. All right, so we had that semicircle, and we were taking a look at the midpoints. And so just a reminder, we are making our rectangles one wide. So this is our partition. And we are picking the midpoints. We're going to trace up from each midpoint. Check out this picture, better than the last one, huh? All right, gotta love technology. Sometimes it's good, sometimes it sucks, but here we are, back together again. All right, so those are my midpoints. These are the boundaries of my rectangle. Here, here, and using my midpoints, these are my rectangles. And we're going to generalize this tomorrow, but let's just play. So we discovered that this one had a height of the, let's see, it was square root of 1.75. And these guys had heights of square root of 3.75 each. And this one had a height of 1.75. Now, since we chose the nice width of 1, and these are also the areas, so we can add those up. So I'm going to whip out my Google calculator. And we'll come back to GeoGebra in a minute. Whoa, what did I do? Stop it. Try again. There we go. So I have 2 times the SQRT of 1.75. 2 of those, and then there were 2 of the square roots of 3.75. So altogether, we get an area of about 6.52-ish, adding those suckers up. So we get an area under that curve of approximately 6.52. We can improve the area. Again, we get a little extra area there. We miss some area there, a little extra, we miss some. So I'm guessing this is an overestimate. It's greater than the actual area. Now we know the actual area because this is a circle. Right? So remember the area for a circle is equal to pi times the radius squared. Now I want a semicircle, so I want pi times the radius squared, but I want to cut that in half. Radius is 2 here, 2 squared is 4, 4 divided by 2 is 2. So I get an area of exactly 2 pi, which is approximately 6.28. So my earlier estimates were a little low, this one is a little high, and it just depends. We have lower sums, which means it's less than. Upper sums are greater than the actual area. And then you have left-hand endpoints and right-hand endpoints. You have, oh, you know what else would be interesting? Check this out, this is cute. Let's see if I can get just that picture. Got it. Tab. Paste that sucker in. There's all kinds of tricks people came up with over the years to do this. So let's suppose we again go to our partition at 1 unit wide. And so, whoa, stop it. Sorry, sometimes I have trouble with my magic pen. Just ignore that. So if I draw a vertical line here, and here, whoa, and here, then I end up with these points on the curve. And so instead of doing left-hand endpoints or right-hand endpoints or midpoints, we could say, hey, just connect the endpoints. And so I could grab this sucker and connect it up there. I should try the line tool on here. Connect that with a straight line. Connect. Oh, this is going bad. Let's undo all that mess. Line tool to work. Boom. Oh yeah, that works. Boom. There we go. Boom. Does anyone know what these shapes are called? Well, Well, the ones on the right and left are obviously triangles. The ones in between, like this one right here, since it has a pair of parallel sides, is a trapezoid. And so if I go with just connecting the endpoints, this uses what's called the trapezoidal rule. There's a bunch of different rules for accumulating, approximating areas. Cool thing, a lot of math tools have those built in. So for example, let's check out GeoGebra for a minute. Here's my curve in GeoGebra. And so I'm going to ask GeoGebra if it has any tools that have anything to do with rectangles. It says that there, it has a function called rectangle sum. Ooh, let's try it out, see what it does. Click it, it says, what's your function? Well, my function is called f, tab. What's my start value? I'm starting at -2. What's your end value? My index value is +2. How many rectangles do you want? Well, I would like 4 of them. Position of the rectangle. And GeoGebra, I looked this up ahead of time, says left endpoints plug in a 0, right endpoints plug in a 1, midpoints would be a 0.5. I'll go over that again later. So let's suppose we want to go with midpoints. That was the last one we did. So I would say click the rectangle's height in the middle. Ooh, look at that. It's drawing the rectangles for me. Isn't that cute? Then I hit enter, and it says, hey, the sum of those rectangles is 6.52. That's displaying that number right there for me and up here. Cool thing about GeoGebra is I can say, ooh, let's dive in a little farther. 4 was quite a bit of work to do by hand. 8 would be even more work, but GeoGebra, all I do is change the 4 to an 8, and it automatically draws the 8 rectangles, tells me what the area is. GeoGebra says it's 6.37, getting closer to the actual. Well, if I have a computer that can automatically draw them for me, why mess around with 8 when I could do 100? 6.29. I could also ask GeoGebra to give me more decimals. So options, rounding. I could say, hey, give me 10 decimal places. 6.285. Ooh, that's pretty close. Let's blow up the font to try 18, a little better. Why stop at 100? Could GeoGebra handle 1,000 little rectangles? Oh my gosh, pretty much colors in. 6.2832. What is 2 pi? GeoGebra or Google 2 pi 2832. Hey, that's pretty good. Well, it took me 1,000 rectangles to get there. Not bad. So our goal is to take the idea of these rectangle sums. Let's get down to one that's more human readable, like 8. And we're going to figure out how to generate these with mathematical symbols. And then what we want to do is we want to let the rectangle width get smaller and smaller and smaller and smaller. And then what that will lead us to is a pattern, a limit that will take us to the actual sum. So that's our goal. Just like you use the difference quotient with derivatives and limits, here we're going to use the sum of areas, of little teeny areas, to build up big areas. And we're going to look at limits to see if there's a pattern. And that is the birth of integration. Wicked cool, huh? All right, I'm going to cut this off now. We'll pick up with more of these crazy fun sums and some new beautiful notation to go with it tomorrow. So have a good day. Jump in this chapter 5, section 1. Do good math. Stay in touch. Bye-bye.